Hello everyone. Today I am going to talk about gas chromatography. Gas chromatography is one of the most versatile and ubiquitous techniques in the laboratory. It is used for the determination of various kinds of organic compounds. It is extremely used for the separation of organic compounds like benzene and cyclohexene, which have almost nearly similar boiling points. And these compounds are extremely difficult to separate by simple conventional distillation processes. There are basically two types of gas chromatography: gas solid chromatography, which is also known as adsorption chromatography, and the other one is and the gas liquid chromatography called the partition chromatography. So I'm going to discuss about the stationary phases used in gas chromatography. The particle size of the stationary phase should be passed through a mesh size of around 80 to 120 micrometer, and the particle size should be nearly around 125 to 180 micrometer. There are three types of stationary phases. Uncoated solid material. Examples of such stationary phases are activated charcoal, silica gel, alumina, and low molecular weights compounds like alcohols and water can be separated using styrene and divinyl benzene as the stationary phases. And the second type of stationary phase is inert solid coated with a layer of liquid. The example of such stationary phases is diatomaceous earth, which is coated with 1.1 to 1.5% of silicon polymers, such as having functional groups like phenyl, cyano groups, and trifluoropropyl groups, and ethylene glycol. The third type is direct coating of the liquid using silicon polymers and ethylene glycol. So we are basically going to talk about liquid stationary phases. Liquid stationary phases are selected based on the polarity determined by the relative polarities of the solute. It is selected on the principle of like dissolves like. That is, a polar stationary phase will interact more with a polar compounds and vice versa. A phase should be selected in which the solute has some solubility. Non-polar liquid phases are generally non-selective because there are few forces between the solute and the solvent, and so separation tend to follow the order of boiling points of the solutes, with the lower boiling ones eluting first. Polar liquid phases exhibit several interactions with the solute, such as ion-ion interactions, ion-dipole interactions, dipole-dipole interactions, hydrogen bonds, and induction forces, which have often no correlation with the retention factor and the volatility of the solutes. Most commonly used stationary phases, liquid stationary phases are polysiloxanes in gas chromatography. Polysiloxanes and polyethylene glycol. Polyethylene glycol is also known as carbox, having stationary, which are used as stationary phases, as they have very high molecular weight, very high molecular weights, and they are also thermally stable, and they exist as liquids and gums. Polyethylene glycol, which is also known as carbox, are specifically liquids at their operating temperatures. Siloxane polymers strengthens and stiffens the polymer backbone and exhibits stationary phase degradation at higher do not exhibit stationary phase degradation at higher temperatures, and results in a lower column bleed. Here, column bleed refers to the low to the less amount of less vaporization of the stationary phase. So I have prepared some notes of polysiloxanes and their backbones. Here polysiloxanes, the polysiloxanes have a backbone, as I have shown in this figure here, having oxygen group and silicon, and two R groups are attached here. These R groups are R1 and R2. The R functional groups determine the polarity and include methyl, phenyl, cyanopropyl, and trifluoropropyl groups. Those with the cyano functional groups are susceptible to attack by water and oxygen. It's because we know that cyano group are quite hygroscopic in nature, so they are not particularly preferable for such gas phase chromatographic techniques. Now I have prepared some phase of the stationary phases, the polarity of those stationary phases, their uses of the stationary phases, and the maximum temperature that is used in the operation of such stationary phases. First is 100% dimethyl polysilane, which is a completely pure polysilane derivative, and it is a polymer which is completely non-polar and is used in general purpose phase for routine use like hydrocarbons, polynuclear aromatics, etc. Here HC is hydrocarbons and PNA is polynuclear aromatics. And the maximum temperature range is of around 320 degrees Celsius. The second one is diphenyl methyl dimethyl polysiloxane. Here first X is the percentage, and the second X also from that percentage we can determine for a low low polarity compounds X is around 5%, and for intermediate compounds X is around 35 to 65%, and it is basically used for pesticides. And the temperature range is for low polarity the temperature is 320 degrees Celsius, and for intermediates it is ranges around 300 to 370 degrees Celsius. The third is of the type 14% cyanopropyl phenyl and 86% dimethylsiloxane. It is also a polymer having the CN functional group, so it will be quite hygroscopic in nature, and hence the polarity is of intermediate type. It is used in the separation of organochlorine pesticides like DDT, and it is susceptible to damage by moisture and oxygen, as the cyano group is present, and the maximum temperature is around 280 degrees Celsius. The fourth type is of 80% bis-cyanopropyl, 20% cyanopropyl phenyl polysiloxane. It has three cyanopropyl groups, which is for which it is quite hygroscopic in nature, and this compound is very polar. And this is used for the separation of free acids, polysaturated fatty acids, and alcohols, and the temperature is around 275 degrees Celsius. For very polar compounds, the maximum temperature ranges are quite small. The fifth type is of arylenes. Here R1, R2, R3, and R4 are the alkyl groups, or this can be aryl groups also, and the polarity varies as the R groups varies, and it is used at high temperatures, and it is of low bleed type, that is loss of stationary which is bleeding in column. Bleeding in the column means that is the loss of stationary phase by vaporization. So here this process is quite low, therefore it is useful, and the maximum temperature is 300 to 350 degrees Celsius. The sixth type is of carboranes. Here I have drawn an icosahedral structure of the boron 12 class, and two carbon groups are attached, which is two carbons are attached, which are of dark circles, and the white circles are borons, and near the carbons the silicon derivatives are attached, and they form a polymer. This is the carboranes type of stationary phase. Here on changing these alkyl groups, we can not only use CH3 groups but other groups also. So on changing these alkyl groups, their polarity varies. They have a very high temperature similar to arylenes, and they also have low bleed, and the maximum temperature is around 430 degrees Celsius. The last two types are of polyethylene glycol, which is also called carbo-wax, and it is particularly liquid in their operating temperature, that is the maximum operating temperature of 250 degrees Celsius, and is extremely polar, very polar, and it is extremely useful for the separation of alcohols. That is, I have written the groups here: OH groups, CHO, aldehyde groups, ketonic groups, and separation of aromatic isomers, example like xylenes. And last one is ionic liquids. Here I have given a structure of an ionic liquid of phosphorus and OTF. I have drawn the structure here, and it is quite polar and is excellent for the separation of alcohols, OH group, fatty acids, methyl esters, aromatics, and pesticides, etc. And it has a maximum temperature of 360 degrees Celsius. This is my talk of stationary phases in gas chromatography. Thank you for listening.